This project started with a simple question. Could a conventional cast gem handle be made lighter and more distinctive for metal 3D printing without changing the way it worked? To explore that, I used Fusion Generative Design to rebuild the structure around its functional requirements. The client supplied step files for the main attachment and the handles. These files defined the important dimensions and the way the product would be assembled. The handles would be machined separately and bolted onto the printed part. The 5 carabiner holes also had to keep their exact dimensions and positions because they allow the user to connect the cable at different angles. After moving into the Generative Design workspace, I use Edit Model to create the additional geometry I need from the client's step file without altering the original design. Here I'm defining the preserve and obstacle regions. Preserve geometry tells Fusion which areas must remain in every outcome, while obstacle geometry defines the spaces that must stay empty. Based on these regions, together with the loads and constraints, Fusion explores how material can be distributed between the required connection points. The gray body is the client's original step model. The green regions are preserved geometry. These are the fixed interfaces Fusion must retain and the locations where loads and constraints will be applied. Next, the red obstacle bodies appear. These do the opposite. They reserve the space that must remain empty for the user's hands, bolt installation, and carabiner access. Fusion can generate material around these volumes, but never through them. This prevents an efficient-looking result from becoming impossible to assemble or awkward to use. Together, these regions define the boundaries of the design problem. As I switch the obstacles on and off, the available design space becomes much clearer. Now I define what Fusion is actually optimizing. The objective is to minimize mass, but not without limits. I set a safety factor of 2, limit global displacement to 1 millimeter in all 3 directions, and include a buckling safety factor of 2. For metal 3D printing, I use the positive Z orientation, a 45-degree overhang limit, and a minimum thickness of 3 millimeters. Then comes the part that has the greatest influence on the outcome, the load cases. I created 10 separate load cases across the 5 carabiner holes, using different pull directions to represent how the attachment may be used. These loads are not applied simultaneously. Fusion evaluates each case separately, so the final structure has to respond to every defined direction. Optimizing for only one pull direction could produce a lighter result that becomes unsuitable as soon as the cable angle changes. Fusion does not return one final answer. It produces a set of candidates. Here there are more than 10 outcomes, each showing a different way to connect the same preserve regions while meeting the study conditions. I scan through them first to understand the range of geometry Fusion has produced. Fusion's recommendation engine then brings 4 outcomes forward. They are not selected by appearance alone. Fusion ranks them using the criteria defined in the recommendation settings, including low mass, target factor of safety, displacement, cost, manufacturing complexity, and solver maturity. Because each criterion can be weighted, the recommended outcomes depend on the priorities of the project. In comparison view, a single view cube controls all 4 models. Rotating one rotates the others to the same angle, making differences in their branches and transitions much easier to identify. The results are quite close, so I also use the Properties panel instead of judging them only by appearance. Here I can compare values such as mass, displacement, and factor of safety. After reviewing both the geometry and the properties, I chose Study 16 for the client. Its results were similar to the other candidates, but its geometry was more coherent and consistent, making it the most suitable starting point for CAD refinement. With Study 16 selected, I created the Fusion design and inspected the geometry from every angle. The final form connected the required interfaces while respecting the load cases, clearances, and manufacturing limits defined at the beginning. And then came the best part. The client sent me this photo of the finished design, produced with metal 3D printing. What began as a step model and a set of engineering requirements was now a real physical part. If you have a product idea, a drone frame, or a mechanical component you want to bring closer to production, start at craftcad.com. On the Request a Quote page, choose Fiverr, Upwork, or LinkedIn, or send the first details of your project directly through the project form. Include a short description, reference images or CAD files if available, the intended manufacturing method, preferred material, and any important load, clearance, or mounting requirements. This gives me enough information to understand the scope, identify the main engineering challenges, and recommend the right CAD, generative design, or FEA workflow. When ready, request a quote at craftcad.com.